Hi ladies, this is lesson 2.3 in your Discovering Geometry textbooks, and it's about mathematical modeling. So our last lesson was about using inductive reasoning to predict what the next term in the sequence would look like, and before that we practiced with drawing diagrams. This is going to be a combination of both of those. We're going to use diagrams and we're going to use our inductive reasoning to develop a mathematical model. So to start off this lesson, consider this launch idea. If everyone in the town of Skunks Crossing, which has population of 6, if everyone has a telephone, how many different lines are going to be needed to connect all of the phones to each other, and how do you know? So to start off, let's draw a diagram. So we have 6 people. 1, 2, 3, 4, 5, 6. And we want to know how many phone lines we need to connect all 6 people. So from the first point, here's 1 line, 2 lines, 3 lines, 4 lines, 5 lines. So we have 5 orange lines. From the second point, we already have this first line, so we're not going to do that one again. 1, 2, 3, 4. From our third point, we use green. We already have this first one, we have this second one. There's 1 line, 2 lines, 3 lines. From our fourth point, we already have this line, we already have this line, we have this line already. So here's 1, 2 more. And then from our last point, we have 1, 2, 3, 4, and we need 1 more point, 1 more line. So if we add all of those up together, 5 plus 4 plus 3 plus 2 plus 1, we get a total of 15 lines. So in lesson 2.1, again, we focused on drawing visual models. That's going to be true here still. You want to continue to draw those visual models and then develop a pattern to come up with how many, what your next number in the sequence is. So I could use this to determine how many lines I would need for a population of 100 or 200 people. So we're going to practice drawing or writing out some mathematical models. So again, in chapter 1, we looked at points, lines, planes, polygons, triangles, diagonals. Those are all mathematical models of physical objects. In this lesson, we're going to use more of mathematical models to determine which is the next number in the sequence. So we've got a couple key terms here. The first is triangular numbers. So we're going to draw some visuals here to help you visualize what triangular numbers are. So the numbers below are called triangular numbers because you can arrange them into a triangle, 1, 3, 6, and 10. So here's 1, just a point. Here's 3, 1, 2, 3. Here's 6, 1, 2, 3, 4, 5, 6. Here's 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. 15 is a triangular number, as you can see in the pool diagram to the left. So 15 pool balls can be arranged in a triangle. The next term we have are rectangular numbers. And rectangular numbers are numbers that can be arranged into a rectangle. I'm not able to make my point a little bit smaller, but that's okay. We'll go with the size that we have. So 2, there's rectangle 2 dots. Rectangular number 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 20. 5 by 4. So 5, 10, 15, 20. So our next step is to write a mathematical model to describe how many squares are in each rectangle. Well, first I can look at my number of, it says squares, but I'm really using dots. So in the rectangular diagrams above with the rectangular numbers 2, 6, 12, and 20, I can use this diagram to write a mathematical model and then determine how many dots are going to be in the 25th rectangle. My line is still staying pretty thick, so we'll try to adjust it. So mathematical to describe how many squares are in each rectangle. So first, let's think in the first rectangle, which is the first term, in the second term, I have 6 dots. So instead of just saying, oh, okay, it increases 4 dots, and then it increases 6 dots, and then it increases 8 dots, and then 10, and then 12, and so on, that's going to be pretty hard to determine what the 25th rectangle looks like without actually drawing 25 rectangles and counting all of the dots. So I want to look for some other patterns I see. So in the first rectangle, I see that it has is that true for the second one? It has 6 rectangles, it has a length of 3 and a width of 2. The third one, 12 dots, I see a width of 4, a length of 4, and a width of 3. So in all 4 of these rectangles, I can see that the width, or I'm using width as height, but the width is the same number of dots as the term. So the first term has one width, the second term has 2 width, third term has 3 width. And now how does length relate to that? So in the first term, I have a length of 2, which is 1 plus 2, 1 plus 1. In the second term, I have a length of 3, which is 2 plus 1. And in the third term, I have a length of 4, which is 3 plus 1. And in the fourth term, I have a length of 5, which is 4 plus 1. So I'm going to now be able to write a mathematical model based on those patterns that I see. So I already know that my number of dots is length times width. I'm going to have to move to a different mode here. So I know that the number of dots in my rectangles are length times width. And I know that my length, based on my observations, is the number term that I'm in, plus 1. So again, I'm referring to this as my length, and then I'm referring to this as my width. And I know that my width is equal to n, or the number of terms I'm in. So this is the first term, so n equals 1. This is the second term, or n equals 2. This is the third term, or n equals 3. And this is my fourth term, or n equals 4. So to write a mathematical model to describe how many squares are in each rectangle, I'm going to take length times width, but referring to the number of terms, got n plus 1 times n. So here's my length, n plus 1, and here's my width, n. So how many squares are going to be in the 25th rectangle? Well, I'll take 25 plus 1 times 25, which is 26 plus 1, 26 times 25, and I get 650 dots. Now you try. So take a minute and try this on your own and do the best you can, and pause the video while you work and unpause the video for your solution. So if you're looking at the number of lines, the number of regions, I can look at the first one, and here's one region, and here's the second region. Then I can look at the second one where there are 2 lines, and here's 1, 2, 3, 4 regions. And looking at the third one, 1, 2, 3, 4, 5, 6 regions. With 3 lines. Then if I were to draw 4 lines, and I could do this as long as you need to until you can recognize a pattern. 1, 2, 3, 4. So they're all going through that same point. I can see that there are 1, 2, 3, 4, 5, 6, 7, 8 regions. And I could do it again for 5 lines if I needed to. 1, 2, 3, 4, 5 lines, all going through the same point. And now counting how many regions there are. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 regions. So what kind of pattern do you recognize? 1 line, 2 regions, 2 lines, 4 regions, 3 lines, 6 regions, and so on. So how many regions are there going to be if I draw n lines? Well, 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6. So if I have n lines, I'm going to have 2 times n regions. So how many regions am I going to have for 35 lines? 35 times 2, 70 regions. For the next example, what's the total number of diagonals in a 35-sided polygon? Before we look at this example, let's first consider some triangular numbers. So this is an experiment that we'll do in class next time I see you, but it says each of 30 people at a party shook hands with everyone else. How many handshakes were there altogether? So here's a visual approach to arrive at the rule for this handshakes problem. We can arrange these numbers into triangular stacks, where the first term, so if there was one person, there would be 0 handshakes, but the second term, this is really the second term, and this is the third term, this is the fourth term, and this is the fifth term. So if there are 2 people, there would be 1 handshake, right? Each person would shake hands 1 time. If there are 3 people, then there would be 3 handshakes. If there are 4 people, there will be 6 handshakes, and if there are 5 people, there will be 10 handshakes. So we can use the rectangular numbers that we just developed a model for on a couple slides prior. So we said that with the rectangular model, our model is n plus 1 times n. So the term plus 1 times the term is how many dots will be in the rectangular model. But with the triangular model, we don't quite have the same thing. We need to divide that by 2. So each of these is half of the rectangular model. So in this one, the first term is 0. So each of these are half of the rectangular model. So if our rectangular number is n times n plus 1, then with our triangular number, we have the model n times n plus 1 divided by 2. Just like the area of a triangle is 1/2 base times height, and the area of a rectangle, area of a triangle, the area of a rectangle is base times height, or we call it length times width. So the area of a triangle is half of that. So the numbers in a triangular sequence are half of those in a rectangular sequence. So with this information, go back and look at our triangular models. We increase 2, then we increase 3, then we increase 4. Our rectangular models, we increase 4, we increase 6, we increase 8. So in this diagonals problem, what's the total number of diagonals in a 35-sided polygon? Well, first, let's look. Number of sides and number of diagonals. If it has 3 sides, it has 0 diagonals. If it has 4 sides, it has 2 diagonals. If it has 5 sides, it has 5 diagonals. We can draw a 6-sided figure. Then we can count its diagonals. 1, 2, 3, 4, 5, 6, 7, 8, 9. If it has 6 sides, it has 9 diagonals. So plus 2, plus 3, plus 4. That looks similar to our triangular model. Plus 2, plus 3, plus 4. So we're going to use that triangular number pattern to determine how many sides are in a 35-sided polygon. So our model was the forward one. Our model for our triangular numbers was n times n plus 1 divided by 2. Now it's not always going to be n plus 1. That's what it is for these perfect triangles. But for this case, since we're starting at 3, where our n is 3, and a 3-sided polygon has 0 diagonals, we can come up with this model. The first one, n, number of sides, and 0, divided by 2. We need to come up with a solution 0. So how do we get 0 in this first one? What do we have to do from n? So we have n times n plus or minus something divided by 2 will give us 0. In this case, our first term, or the first number of sides we're working with, is 3. So 3 times 3 plus or minus something divided by 2 is 0. What's true about this? What does that something have to be? Well, if we take 3 minus 3, we have 0 times 3 divided by 2. So 3 times 3 minus 3 divided by 2. That equals 0. 3 times 0 divided by 2. Now let's look for our next term. We're not always going to subtract. In this first term, 3 is the same as n, but that 3 is going to be held constant, just like here, our 1 is held constant. So I'll switch colors, green. So for our next term, where n is 4, we want to say 4 times n minus 3, which is 4 minus 3, divided by 2. We want that to be 2. So is that true? 4 times 4 minus 3, which is 1. So 4 times 1 divided by 2 is 2. 5 times 5 minus 3. So 5 times 2. We want that to be 5. So 5 times 2 is 10, divided by 2. Oops, that equals 5. So for a 35-sided polygon, we can use that same model. And so again, the important part of this is recognizing that this is a triangular number pattern. Goes up 2, goes up 3, goes up 4. So we have to recognize that this is a triangular number pattern before we can write the model n times n minus 3 divided by 2. So for a 35-gon, we have 35 times 35 minus 3, which is 32, divided by 2. And if we calc that out, 35 times 32 is 1120, divided by 2. We get 560. So we don't actually have to draw a 35-gon, although, well, I don't even have the option here. Too many signs. So we don't actually have to draw a 35-gon, and count all of the diagonals. But if we did, we would count 560 diagonals. So this one we looked at it as related to triangular numbers. And again, we'll do an experiment like this in class next time I see you. So to summarize, how is a rectangular array of dots related to the triangular array of dots, so we developed mathematical models for both of those. And how do the rules for rectangular numbers and triangular numbers show that relationship? So again, for the triangular array of dots, we said n times n plus 1 divided by 2 is kind of our generic formula. And for the rectangular, we said n times n plus 1. So anytime we have a triangular array, twice as many of those will give us our rectangular array. So we can take our rectangular array divided into 2, and if we had 2 triangles, that would be a rectangle. So on your own, I want you to try this extra example. If everyone at a party shook hands with everyone else exactly, and there are 406 handshakes, how many people were at the party? So you can use that model that we used in the previous one. It's a triangular array of numbers. And then the closing question. 1, 3, 6, 10, 2, 6, 12, 20. One of these sequences is called triangular numbers and the other rectangular numbers. Which one is which? And explain how you know that. And then if there are any other questions, please jot those notes down and we can discuss in class. Thanks.